Okay, in this video, we're going to attempt a constant acceleration question from a WJC paper from 2013. I chose this one particularly because it is actually quite a tricky question. It brings a lot of the things that people forget about into one which is very seemingly small question, but it's actually a lot of work. So an object is projected vertically upwards with a speed u from point A, which is 2.8 meters above horizontal ground. The object reaches its greatest height of 18.225 meters above A before falling to the ground. Show that the value of u is 18.9. Now the first thing you've got to remember here is that if you're asked to show a value and you're given it, you cannot use it in your calculations. So we've got to basically verify that u is 18.9 without using that fact in my equations. So the first thing to do is to draw a diagram. So I'm just going to draw myself a quick sketch of what's going on. So this object is 2.8 meters above horizontal ground and it's projected upwards vertically with an initial speed of u. It reaches its greatest height of 18.225 meters before falling to the ground. And the only thing we can put in here straight away is, of course, it would be subject to acceleration, which is what slows it down and drags it back down to Earth, 9.8 meters per second every second. So what I'm going to do now is I'm just going to, for part A, write SUVAT, and underneath SUVAT I'm going to write everything I know. And you'll notice when I do this in class, I'll do this every single time because it's a nice easy way of assigning each of your letters a value or a not a value if you haven't got it. So the first thing, S, I'm going to use as 18.225. That's the greatest distance achieved from its projection point where there was a speed u, so I'll fill that in as well. Now the reason I'm going to use 18.225 is when you see the phrase greatest height, that's as high as that object gets before it gets pulled to Earth. And at that greatest height, its speed is 0. It momentarily stops before being dragged to Earth. So v, the final velocity, at its greatest height, we can denote as being 0. And that's something to look out for when you're looking at these questions. Acceleration due to gravity, I'm going to put as minus 9.8 because that's acting in the opposite direction to projection. And we talked about that in earlier videos. And because I'm taking upwards to be positive, acceleration will be negative. And I know nothing about t, so I'm going to cross that out. So I've got I need to find an equation that's got s, u, v and a in it. And if you consult your equations from the previous video, the only one that would work is v squared equals u squared plus 2as. Substituting in, well, v squared is 0, u squared is u squared, plus 2 lots of minus 9.8 times 18.225. Now, what I'm going to do there is I'm going to take that expression over to the other side by subtracting it technically because there's a minus in there to make it positive, and a bit of rearranging, I'll get u squared is equal to 2 lots of 9.8 times 18.225, and that gives me a value of 357.2 when I put it into my calculator, and when you square root you get a value of 18.9 meters per second. So there you go, I've actually found out that u was 18.9 without actually using the fact in my calculations. Moving on to part B, find the time between the object being projected and the object hitting the ground. This is actually quite a trickier concept. So again, I'll just draw a quick sketch, and obviously we're interested in this displacement here of 2.8. We'll talk about that in a second. U is obviously 18.9. And we've got our acceleration pulling the object to Earth at 9.8 meters per second. And we're after the time it takes to get from its projection point here to hitting the ground here. So if I write SUVAT, S is going to be minus 2.8 because I'm taking upwards as being positive. Anything going upwards is positive. U is 18.9. V, we don't know anything about. A is minus 9.8 and T is what we want. And again, you can see you've got 4 elements that you need and one that's irrelevant to us. S, U, A and T. And the only SUVAT equation that will fit that is ut plus a half at squared. So if I substitute in my values, minus 2.8 is equal to 18.9t plus, well, actually it's going to be negative. And get used to halving 9.8 or doubling it, because this will happen quite a lot. So I'm just going to take out that little bit there, and I'm going to say minus 4.9t squared, half of 9.8. Now what we've got here is a quadratic. So what we're going to do next is we're going to actually rearrange it and get it into a nicer format. So 4.9t squared minus 18.9t minus 2.8 is equal to 0. Now, you're being examined on the mechanics element of this question, so I'm thinking that I could put this into the quadratic formula, but that's quite laborious. There must be a quicker way. So the first thing I think I would do is I'd get rid of the decimal points by just multiplying everything by 10. That gives me 49t squared minus 189t minus 28 is 0. And I know that 49 and 28 are in the 7 times table, and with a quick calculation, so is 189. So I can divide through by 7, so 7t squared minus 27t minus 4 is equal to 0. So I'm going to have a bracket with 7t in, because 7's prime anyway, and a bracket with t, and I think we're going to end up with plus 1 here and minus 4 there, which gives values of t equals minus a seventh or 4. Now obviously we can't have minus a seventh as a value, but it might be worth considering where that comes from and what that's about. So my t value is 4 seconds. It takes 4 seconds